I'd like to welcome everybody today to another installment of the HORIBA Instruments webinar series. Today's topic is going to be process control in Jet A fuel production. And the main focus is going to be on Raman technology for that particular application. It's a bread and butter application for us here at HORIBA. I'll be joined by Dakota Morales. He is our resident PhD product specialist, and we'll be going on a bit of a deep dive into the application, into how we do this particular application and how we use the Raman. I'm Lance Isaac. I'm the regional sales manager. National North American sales manager. Sorry, new title, and I keep forgetting. I'll be giving a very brief overview today. If I can get my computer. There we go. I'll be giving you a very brief overview of the products that we do offer, both from our Raman technology as well as our gas analyzers and combustion analyzers. After I get through with that, I will be passing it over to Dakota. He will, as I say, be getting into the nitty-gritty details as far as Jet A fuel production and how the Raman is used. We will have a question and answer session at the end of the presentation. What I would like to ask everyone to do is, if you do recognize a topic or a question that you have, please log it in the chat box, and that will be proctored by Stevie Lee once we are finished, and we will address each and every one of those. Okay, so as we progress on right now, who is HORIBA Instruments Incorporated? Well, we are part of a 5-tier corporation. This division, the one that we're going to be discussing today, is the Industrial Process and Environmental Group. As you can see on the slide, we do have 16 locations. That's across all five business units. The ones that we'll be focusing on today, or that handle specifically the IPE group, are the office in Salt Lake City, which is the global hub for all of our Raman technology. We have HORIBA Instruments Incorporated in Irvine, California. That's typically where our admin, order entry, things of that nature are handled. And then we have our office in Houston, Texas, more specifically Pasadena, which is the site of the our gas analyzer, and our system integration is all handled through that facility. Just a real quick overview on some of our products. We do offer, as I say, we do offer gas analyzers. They are for ambient air monitoring, combustion control monitoring. Some of you may be more familiar with that being called as SEMS, a continuous emissions monitoring system. We do process gas analyzers. We have a portable gas analyzer, which is also RADA certifiable. Kind of a neat little tool. We do full-scale system integration out of our Pasadena office, and we do also have some system integration out of our Salt Lake City office. We do field services as well. We do demolition, we do installation, and again, obviously the main focus for today's presentation is the Raman technology. Just a quick overview of some of our capabilities as far as system integration goes. We can mount things on panels. We can do small enclosures. We can do 3-sided shelters, all the way up to full-scale enclosed enclosures, enclosed shelters. And I think a real benefit to kind of mention to everyone is that is not limited to HORIBA products. So if you have an alternative vendor that you're interested in, perhaps maybe getting either a sample system or a flow cell enclosure, or say you have a mass spec, an online mass spec, or even a different vendor SEMS that you'd like to incorporate into an enclosure, we have full scale capability to be able to do that. Okay. So today's topics obviously will be focused on the process Raman products. We have a few different offerings. For our online process, we have a single point and a dual point measurement system. We can extend the single point up to 8 channels using a multiplexer, or if you really want to go big, we can do one analyzer can handle up to 17 sampling points. As far as sample options go, we have flow cell enclosures, both high temp and low temp offerings on that as well. And then we also do have immersion probes that can fit directly into your pipeline. There are a large number of our customers who actually begin with a laboratory Raman analyzer. This is a benchtop unit that will fit into your lab. Sometimes it's used for verification, just to make sure that things are running well with the process system, or if you need to do your modeling, how that's typically done. It's typically you would upload some files from the lab unit. That information would be sent to our facility in Salt Lake City. We update the models, we send them back to you, and then you can upload them both to your lab and to your process system. We have a couple sampling options there as well. You can see we have a liquid auto sampler off to the left, and then down on the bottom right, there's a sample tube. I personally call them sample bombs. I don't know how well that's received, but that's just kind of the generic name for what those are. So we have a couple different options from that perspective. Just a few pieces of contact information. Kevin Fouché, who's across the pond this week doing some European work with our counterparts over there. He's our vice president and general manager. Giancarlo Aguirre, he is the head of all operations out of the Salt Lake City office, specifically the Raman group. Again, Dakota, he is our PhD product specialist and overall Raman guru. You can see his email is there as well. We have Mike Ellis, who is our new regional sales manager. Mike's been with us, I don't know, about 2 months. He works very closely with me for us to be able to cover all of our North American customers. And then obviously there's me as well. You have these email addresses that are on here. We encourage you to use them if you have any questions as we go along here. And then finally, I want to make sure that you all know about our social media platforms: YouTube, Instagram, Facebook, TikTok, and LinkedIn as well. This particular webinar will be posted up on our YouTube page later in the week, or at the very latest first part of next week, once we've scrubbed out all my mispronunciations and things of that nature. Okay, so without further ado, I'm going to pass it over to Dakota, and he can dive into Jet A. Dakota?
Thank you, Lance. All right, so welcome everyone. Today we are going to focus on Jet A fuel blending, but definitely from a much more technical and process-oriented perspective. So most people in this audience definitely know what Jet A is, but I think a more interesting question and topic to think about is, how can we control Jet A better while it's actually being produced? Because blending Jet A is definitely not just a fixed recipe, especially in today's world. It's really a live process. So, right, like a crude slate can change, and then suddenly the kerosene cut that's coming straight from the crude unit is going to behave a little differently. Then the hydrotreater may be running at a different severity, maybe because catalyst activity has changed, or just hydrogen availability is different that day for that blend. A take movement may bring in reblend material back into your system that looks really close on paper, but of course is still going to shift your freeze point, flash point, aromatics, etc. So the challenge is not just, can we make on-spec Jet A, right? Like, the real challenge for our customers today is, can you keep it on spec without giving away more quality than you need to, right? That's the name of the game. So when I'm talking about giveaway, right, of course I'm referring to the idea of producing fuel that is better than required by more than necessary. So that's a really safe practice, and it sounds safe, and it is, but it's also really expensive to do that. If you were using more hydrotreated kerosene than needed just to create extra cushion, that quality has value, and it may be better used somewhere else in the refinery than the product that you're making right there. So what this presentation is going to go through today is, answering the question of what changes when Jet A producers can actually see quality in real time instead of waiting for delayed lab feedback. And that's precisely where our HORIBA Process Raman fits in, not just as another analyzer you throw online, but really as a solution to support faster and better informed process control. But before we get into the analyzer itself at all, we're going to start with why this matters economically right now. So Jet A in 2026 is a very hot topic. So actually just a few days ago, the International Air Transport Association, or the IATA, which is a representing body that advocates for global standards for efficiency, security, safety for commercialized aircrafts and businesses and the resources that they need, released their global outlook for air transport for the rest of this year and looking into 2027. So this was really aptly and very timely released for me today to talk to you guys. So, the story here is actually really simple. It's just that Jet A is being produced in a market where the cost of being conservative is getting higher and way less forgiving. So the first number that I want to go over here, is so far this year, just from January to March, averaged this year in 2026, there's about 1.6 million barrels per day of US kerosene type jet fuel products supplied. So this really gives us a feel for how much finished product is moving into the market. So very obviously, this is not a small specialty stream. This is very high volume. And when we are working at that scale, even small improvements in blend control become very, very meaningful rapidly. So for example, if a refinery is consistently giving away extra freeze point headroom, that's going to look really small on a certificate of analysis for sale, But across thousands or millions of barrels for a company, that extra quality cushion actually represents real value over time. So then we have this number down here, projected global airline fuel spend, which is about 350 billion USD this year. So this matters because fuel is certainly one of the largest operating costs for airlines. It's about 39%, projected to increase just from last year itself. So when jet fuel costs increase, that pressure does not just stay with commercial airlines. That moves to you. That moves through the entire supply chain, from the airlines back to the terminals, back to the suppliers, back to the refineries. So if airlines are under way more fuel cost pressure, refiners also then feel that pressure to produce Jet A more efficiently, release product quickly, and then avoid unnecessary rework. So fuel is also expected to represent about 31.4% of airline operating costs this year. So the whole system, is going to be very sensitive to these fuel economics. And then down here, this is the real kicker and point, I think, is that the punchline really is that the projected average jet fuel pricing is around $152 per barrel in 2026 is going to be the predicted average, which is much higher than the $90 per barrel that was, averaged in 2025. So what does that mean for blending, It's clear that for blending, it just means that every barrel is more valuable. Every unnecessary degree of freeze point cushion, every extra flash point margin, every reblend, every delayed release has a bigger economic impact today than it ever did before. And so a delayed lab result is not just an inconvenience or an annoyance for a team or for a refinery anymore. If a tank is sitting there waiting for confirmation, or if operators are blending conservatively because they don't have that real-time confidence, then that delay turns into a margin problem. So it's not just, fuel is expensive. It's when fuel is expensive, slow quality feedback becomes a huge margin problem. So if delayed feedback is a margin problem, the next question really should become, where does that money actually disappear during blending for that margin? So there are three really big places where blending economics can get hurt, starting with giveaway, going into off-spec or reblend risks, and then of course, very obviously a labor burden. But we can start with giveaway over here on the left. So giveaway happens, when a refinery blends more conservatively than it really needs to, because there's uncertainty in the current product quality. So for example, if freeze point is the property everyone is worried about that day, the blend may be pushed farther below the limit than necessary. And so that may mean using more high quality hydrotreated kerosene or avoiding a heavier stream that could have been used economically if there was better real-time visibility. And so that cushion, in our industry, we call that headroom, which is just the safety buffer between the actual product quality and the spec limit. But, some headroom is always going to be necessary. Nobody's ever going to want to cut Jet A, diesel, gas, whatever your final product might be, too close. But too much headroom is undesired as well. So the product passes, but the refinery may have left margin on the table. So that's not great. The second issue is off-spec and reblend risk. So off-spec just means that, obviously the product is failing or failing one of more quality specifications. So for Jet A, that can be freeze point, smoke point, aromatics, sulfur, flash point, or other key properties that refiners care about and customers care about. A practical example, would really be like light end contamination that's going to pull flash point in the wrong direction, or a heavier kerosene contribution that's going to erode all of your freeze point headroom if you put too much into it. If that is not caught until after the tank is already blended, or we'll say maybe 80% blended, now the refinery has to connect it or correct it afterwards. So then they have to reblend. Maybe another stream has to be added. Maybe the tank release is delayed. Maybe material has to be recycled, etc. Whatever that is, it adds time, complexity, cost, things that refiners don't want to deal with. And that problem really becomes timing. If lab feedback, after the blend has already moved, operators may not see quality drift until it's already, too expensive to correct later on anyways, which brings me directly into, my next point of labor burden, which is, the laborious side of things. So traditional quality control often depends on grab samples, manual handling, lab testing, and communication back to operations. All of that is necessary for, getting your certificate of analysis, meeting your ASTM things, all of that is necessary. But for example, right, if you have a grab sample that might represent what was happening when it was pulled, but by the time the result gets back, the blend ratio or whatever you're looking at may have changed, the feed quality may have shifted going into the blend, or a tank movement is already underway that you just didn't see until later. And so this is the gap that real-time monitoring with HORIBA really helps close. So with real-time data, you can tighten quality margins, catch drift earlier, reduce routine manual sampling burden, things like that. So the main important idea for all of this, right, is that real-time data is not just telling you the quality of the recipe or of the blend that you're looking at. It changes when you can act on it as an operator. So now that we've talked about where money is lost, we should look at why Jet A blending is so easy to overcorrect in the first place, more so than gasoline or diesel. So really getting into these ideas of, control pressure points for Jet A blending really describes why Jet A blending is tricky, because these properties that matter definitely do not all move together perfectly at all. A change that helps one property certainly can hurt another. So for example, right, bringing in a lighter component may help with cold flow behavior, but it also creates concern around flashpoint, right? I touched on that a little bit earlier. So one major pressure point is aromatics and naphthalenes. So this is important because they affect combustion behavior, smoke point, and overall fuel performance. And right, just as a reminder, smoke point is a combustion quality measurement related to how cleanly the fuel burns, and these are going to directly impact that. So if the crude slate changes or if hydroheating severity changes, that is directly going to affect the amount of aromatics and the naphthalenes behavior, and that will change too. So a practical example in real life, right, would be a hydrocheater running less severely than normal. So maybe because of unit constraints, the catalyst is aging, or hydrogen availability, whatever it might be. The fuel may still look very close overall, but aromatic content is going to shift as a result of that. And that's going to show up later as an effect or as a result in your smoke point pressure. So another pressure point is flash point margin. So flash point is the lowest temperature where the fuel can give off enough vapor to ignite under your test conditions. And so for Jet A, this is a major safety related property. And flash point is going to move very quickly if light ends get into the jet cut, or if too much of light ends get into the jet cut. So if kerosene cut has too much lighter material carried over from upstream fractionation, then that's going to pull flash point down way faster than operators may expect. And then the lab testing, for this flash point from your Penske Martins or whatever the, test method that you're using to verify this can take time. and you will get that delayed result much later for an operator than an operator may need or want. And then, of course, very important is freeze point headroom. So freeze point is a temperature where wax crystals or solid phases are going to begin to form. So for aviation fuel, whether that's for the military, commercial, whatever that is, right? That's very critical because fuel definitely sees very low temperatures at flying altitudes. So freeze point depends very heavily on composition. Things like the paraffin, isoparaffin ratios, and trace heavier components that get put into the fuel. So a real blending example would be like a heavier kerosene stream becoming more attractive because it's available, right? But if too much goes into the blend, then the freeze point margin is going to start disappearing. And then you're getting your sampling lag. So that's the delay between what is actually happening in the process and when the operator gets usable quality information. So all of these things, the smoke point, flash point, freeze point, all of them are going to be affected by each other and by what is, comprising of the fuel itself. So if there is a lab cycle that is slower than the process dynamics, which is almost always the case, this is where a lot of conservative blending comes from. So if the lab result is behind the process, the operator has to protect the product by building an extra cushion to make sure that everything is going to be okay by the time the blend starts seeing, its finishing parts. So that's logical, right? That definitely makes sense, but it also creates giveaway unnecessarily. So the key takeaway here with these pressure points for Jet A control is that Jet A blending is always a moving target because of all of these properties that are important for speccing the jet fuel. Real-time data can help operators see that movement for all of these instead of just checking the result during or after the fact at a delayed, time. So that difference actually looks like this in practice, where this plot on the left here is really about timing more than anything. So if you just imagine on like this x-axis here of this plot being like the blend time or the time of the blend or the blend progression, I guess, or minute by minute or sample by sample. And then the y-axis can represent the quality of the properties that you might care about for your Jet A, right? So it could be your freeze point, flash point, aromatics, or whatever, right? The black points on here represent, the idea of traditional lab-based measurements, where those measurements are going to be accurate, but they are discrete. They are placed, and spaced very far apart, and they're going to come with some delay. So with lab data, you may know where the product was at a certain point, but you may not know where it is right now or where it's heading, which is truly the most important part of blending, right? So a really practical example would be something like tracking freeze point. So the lab result could come back and say the sample was safely on spec at one moment, but during the time it took to manually pull the grab sample, run the method, validate it, communicate it back, the blend is going to have to, may have already be shifted because something else got introduced into the tank or something changed the composition. So that's where timing matters, right? So if this upper boundary here is the off-spec risk zone, that's where the property is getting too close to a spec limit. And then down here at the lower boundary, which is the giveaway zone with a little present, that is where the product may be better than required for the customer, but potentially way more expensive for you than would be necessary. So the middle target region is where any refinery operator or process manager wants, their process to stay safely on spec, but not overcorrected. But with HORIBA Process Raman, what we allow our customers to, sort of find a solution for in all of this is really the idea of frequency and visibility. So instead of waiting for the next lab result, these blue dots can represent this idea of an operator getting a much more continuous view of the process. They can see whether the process is drifting towards an off-spec risk zone or going to, give away, too much of their margin. And that is truly the real value of our HORIBA Process Raman. It's not just that you get a number faster or something like that. It's just that you can actually see direction. You can see of your blend, and you see whether the process is stable or starting to drift before that drift becomes way too expensive or way too much of a mistake later on. So if like Flashpoint, right, is gradually trending toward a limit because light ends are slipping, then Raman, can give the operator a chance to see that trend developing. So without that real-time visibility, the first clear signal may be a lab result that just arrived a little bit later. So that's why I like to say this over here on the right, is that traditional monitoring definitely tells you what happened, but we can show you what's happening. So it's this idea of being proactive and reactive. So the other important point too is that our Raman here can support an all-in-one measurement approach. So one Raman spectrum, can be used to predict multiple Jet A quality properties, which we'll get into in a second here. So instead of treating quality as like a single lab number or, a combination or a weighting of several different lab numbers that's going to come to you at a certain time, you can really reduce that property scatter, and you can operate closer to the ideal window with way more confidence with that real-time visibility. So control is not just knowing what the final answer is going to be from your lab or what that final number might be for a certain property. Control is really about empowering our customers to know the direction early enough to do something about it. So the big shift here, right, is getting away from this idea of lab-only feedback or dealing with costly or, interrupting, physical property analyzers to proactive real-time process control. And the word proactive is probably the most important word here on this slide. And what we really want to try to communicate to you guys with this webinar is that with lab-only feedback, the workflow is often blend, sample, test, wait, respond, right? And then just repeat that cycle over and over again. And that works, obviously. It definitely works, but it can be slow. But with real-time Raman data, the feedback loop gets much, much, much shorter. And I'm talking like down to seconds of measurements. So a feedback loop, right, is this idea of, a cycle of measuring the process, interpreting the result, and then making that adjustment. So the shorter that feedback loop is, the faster that operators can correct themselves or the blend. And so that's exactly what we mean by being proactive versus being reactive. The operator is not waiting until the blend has already landed outside the preferred window. They can see the process while it's still going. So the more visibility you have across the system, the easier it is to understand like what is driving final quality. And so that data needs to connect into your plant workflow, right? So that may mean sending information to the DCS, which is the main, platform that you're going to use to monitor and control the plant, and then that can be connected into your APC or your advanced process control, which is using our chemometric models or your own refinery models and control strategies to optimize the process more automatically. So a practical example of like our customers when they do this and they connect our analyzers into their plants is, using our Raman predictions and measurements as a part of their control strategy that can adjust blend ratios by seeing the full blend system while still keeping freeze point, flash, smoke, and aromatics inside of your target window for that product. So the reason this matters is super straightforward over here. It's just those 4 points really that can just be reiterated over and over again. And it's important to say this very clearly, is that Raman is not going to, replace an operator, replace a project, operator or anything like that. It just gives the people that matter the most that visibility. So the people that are running those, manual tests in the lab, the people that are, telling the lab folks like, hey, we need this tested, or can you check this? The people that are controlling off of the DCS or the APCs for those blend ratios. All of those people matter the most for these sort of blends. And this process Raman, whether that's in the lab or online, can give all of those really important folks more oversight and more details into things that, they're getting paid to care about. So that's really the value proposition. So we can really look at where this can actually be installed in the blending system to kind of give all of those people that oversight that they really need. So this is just a really simplified illustration of like a Jet A blending system. So you have different blend sources, right? You have like your straight run kerosene, your hydrotreated kerosene, heavy cuts, your additives, depending on, where this fuel is going, and then of course your recycled or reblended material. And all of these, right, can be fed into your, can contribute really into the final Jet A blend. And the measurement points can represent here, like these little flow cell enclosures, which we'll get into in a little bit. These flow cell enclosures represent measurement points that our customers like to put our Raman on. So these can be individual feed feed streams, excuse me, the blend header or the final blend line itself. And this little red line here that you see from the sampling points is the fiber optic cables that connect the Raman probes inside the sample enclosures into the analyzer itself. So the really important thing here is that the analyzer is not just generating spectra in isolation. So if we're collecting Raman at all of these points, right, we're not just producing a pretty Raman picture, right? That's just going to sit on the analyzer. The measurement of that spectrum can be translated into real predictions for properties and components that our customers care about, and then be connected back into your control room and then the DCS to an APC system, something like that, so that the information actually becomes actionable. So really the main point, right, is that our HORIBA Process Raman is more than just creating, a spectrum or using spectroscopy, to generate a spectrum. We're really providing information, and we're just using Raman to give you that information. So you're not only checking the final tank after the fact, you're not just, looking at the feed streams changing, you're seeing how the blend is being created by implementing Raman in such a way that's being shown here in this illustration. So this is the actual measurement concept, right? So over here on the left, this big plot right here is the Raman spectrum of Jet A. The x-axis here is the Raman shift, or the energy, that is representing that Raman transition or vibration at that energy. So Raman shift, right, is basically telling us the energy difference between the laser light going into the sample and then the scattered light coming back. But in non-technical, very practical terms, it just means that different positions on the x-axis correspond to different molecules. The y-axis over here is the Raman intensity. That tells us how strongly the sample scattered light at each Raman shift or Raman energy. So the peaks and the dips and everything that you see in the spectrum are not random. They are giving us very defined information about the chemical bonds and molecular structures in the fuel. Right, so that's a very important point, because Jet A is a very complex hydrocarbon mixture. The spectrum of Jet A is going to contain contributions from paraffin, isoparaffins, cycloparaffins, aromatics, other hydrocarbon structures, right? A whole different classes of molecules, and then all of those classes are going to have their individual components too. And this is very important, right? Because all of these important Jet A properties are tied to those compositions. So a shift in the relative amount in aromatic content can affect smoke point. A change in heavier hydrocarbon content can affect freeze point or that distillation range, right? And so this is some really nice, benefits of Process Raman for our customers here. Because if we have about like a 30-second online measurement, which is exactly the time that it took to generate this spectrum and then get the results for the customer, right? It changes the timing of quality information. So instead of waiting for the next lab cycle, the analyzer can just provide you a new update every 30 seconds directly from that process itself. So this supports the prediction of key Jet A quality drivers like freeze point and flash point. It also allows measurement before and after additives are added for different grades. So, if a fuel line is going to, a military operation or something like that, and a refiner needs to add additives after the fact, Raman can see through those additives. We can see the quality of those additives. We can see what those additives are changing with our Raman. For commercial uses, right? If SAFs need to be blended into that jet fuel for EU standards for commercial aircraft or cargo aircraft that is going to land in Europe or in the EU, I should say, we can see that blend ratio between SAFs and Jet A with Raman. It's these sort of before and afters Raman can also empower our customers to look at. And it also can help monitor unit performance, such as the hydrotreater, right? You can very easily put Raman on before and after a hydrotreater, or even just the after hydrotreater line, right? And you can still see, the facts of the matter from that. So if the hydrotreater, right, begins operating at a different severity, the Raman spectrum may reflect the resultant chemistry change before that change fully shows up as like a final tank issue. So that really gives the refinery a better chance to understand whether a quality shift is coming from feed quality, like a hydroheating severity, blend ratio, or another process change. So the biggest idea here, right here in this bold, is that we're getting quality by control instead of quality by testing. So quality by testing is this idea of you make the product, test it, and then find out whether it passed. Quality by control means that your operator is steering the process while the fuel is being made. That is a much, much, much stronger operating position for engineers at a refinery. So then, the obvious question is at this point, how much information can one Raman measurement actually provide? So over here on the left, this table is an example of the kind of multi-property quality profile that our HORIBA Process Raman can support from one online analyzer, all in just one measurement. So these are Jet A related process measurements and observed ranges for a real customer process that they allowed us to use to show you today. So for example, for this blend that they were using, smoke point was ranging from about 15.9 to 25 or to 24.5 degrees Celsius. We can get down into our flash freeze, sulfur contents, total aromatic saturates, our distillation curves, things like that, because these are going to help describe the volatility in the boiling range of the fuel for sure. And then if the front end of that curve changes, that could relate to lighter material flash point. If the back end of that changes, that could relate to heavier components or the freeze point, right? So this is the fact of the matter, is that you can't think of Jet A quality as just one number, but when you look at all of these properties, it gives you a much fuller picture of the moving target for this Jet A product. And that's the key point, right? Is that you can get 25 plus important Jet A parameters from one 30-second measurement. And these parameters or properties are defined by our customers. They tell us what they care about. They tell us what they want to measure. And we can build those calibrations, build those models based off of what every individual customer needs for that sampling point or for that product. Because a refinery does not only just care about one of these things, it's a full picture for how all these properties move together and how one decision affects the entire blending quality picture. So Raman with HORIBA becomes very powerful here. It gives your process team a multi-property view just from a single measurement in 30 seconds. So after blending, right, the question becomes, how do we keep confidence in that finished product, or right before the custody transfer, right before it gets put into a pipe or something, right? This is where non-invasive product tank monitoring becomes valuable. HORIBA Process Raman itself is inherently non-invasive, so we don't, need to consume manual samples to get you your data. We don't need to chemically change anything. We don't need to vaporize anything. We don't need to destroy your sample. So it's really nice that we don't need to chemically change any of your fuel to get the answers that you need. So, a practical example, right, would be what I just said a little bit ago, is like a product tank that has already been blended and is just waiting for release or transfer later. The refinery is going to want that confidence that the product remains stable, that no unexpected contamination has occurred, and that the quality profile is still matching what's expected, right? I'm always double, triple checking all of my results, and I know that refineries are doing that to a much, much higher degree in their labs and online. So this process Raman can really help monitor quality changes over time. So another really important point that we want to make here too is that water contaminants and Jet A processes are real and they do exist, but Raman spectroscopy is blind to those water contaminants. So our spectra is not too affected just because Raman spectroscopy is insensitive to water presence. So we don't need to coalesce or dry any lines with our sampling condition or with our sampling systems. We can just take your sample as is and just take, any sort of contaminations like water within the fuel, because Raman spectra are not affected by water, because this Raman peak over here appears at much higher peak shift than any sort of analytical part of the Raman spectrum that we care about, that we would use to get, the data that our customers really care about. So just a quick refresh before we get into the real specifics of our process Raman products here. Over here on the left is an overview of what we offer online, right? So for our process Raman analyzers, the most straightforward, budget-friendly, and easiest, to implement for our customers are our single and dual point measurement systems, and they do precisely that. If our customers only want to measure like after their blend header, or maybe just one component, or maybe a dual point measurement where they're looking at 2 points before and after hydrotreater, before and after a blend header, whatever that might be, this allows our customers to do that very efficiently. And these are sort of like what we would consider our flagship products. For our customers that want a much heavier hand in their oversight for their processes, they can upgrade their single point measurement systems with a fiber multiplexer, which is this little guy right here that you can see in this picture. It can just be installed very modularly, so you can upgrade this and scale up as you and your refinery needs to. And you can extend this to 8 or 17 more sampling points, just depending on whatever the customer may need for that process. With our sampling options, which I'll get into on the next slide here, we offer a flow cell enclosure, which we recommend for Jet A blending, which I will explain why just on the next slide. On the right here, we have our QC, QA process Raman products. So these would exist within our laboratory, or within a laboratory at a refinery, I should say. And so these Raman analyzers are designed to take up as little real estate as possible on your lab bench, and then also be able to be connected into our liquid auto samplers or our LPG auto samplers, just for routine laboratory process Raman analyses or chemometric model building or support for our online solutions. So getting into our flow cell enclosure here, this is a NEMA 4X rated enclosure, and the dimensions here are about 20 inches wide, about 24 inches tall, and 7 inches depth. So basically, you would just imagine it's basically probably a little bit bigger than your shoulder width if you're just standing in front of one of these. So it's very straightforward and simple. As you can see here, there's absolutely no sample conditioning system that comes with our process Raman, just because we don't need to condition your sample. We very happily take your sample as is. All we need is to borrow it for a few seconds, and we accomplish that by this. We pull in your process line into our flow cell enclosure, and we can pull it up into our flow cell right here that I'm circling with my mouse. And then this image right here in the bottom right is a cut through of that flow cell. If you were to take this and just slice it in half, this is what you would see. Our Raman probes get installed in parallel to this line right here. And in this configuration, we put the probe behind a sealed sapphire window so that the probe is completely protected from any sort of liquid or contamination or anything that may flow through your process. And so as the process comes up through here and then takes that sharp right turn, as you can see, this is where we do our Raman measurement. So it's right at that turn. And when we do that Raman measurement, we can collect the Raman signal and bring it back to our analyzer with fiber optic cables. And that analyzer can be up to 350 meters away from the sampling point. So this really allows for very flexible placement of these flow cell enclosures relative to the analyzer itself. So after the process flows through the flow cell, we just continue to move it through an electronic flow meter that we can then communicate back to our Raman PLC, Modbus, whatever, so that we can tell our customers flow on, yes or no. And then we just flow it right back out into your process line. So we really only need to borrow your sample for a few seconds. We don't need to change anything about the sample. We don't need to heat it. We don't need to cool it. We don't need to pressurize it. We don't need to vaporize it. We just take your liquid as is. And a really, really big and very nice benefit of why we recommend our Jet A customers use these flow cell enclosures for our sampling needs is this right here, our grab sample drain that comes with all of our flow cell enclosures. So our customers can actually pull grab samples from our flow cell enclosures for their labs and for their own testing purposes, which is an extremely, important benefit here because of this electronic grab sample detector. Our electronic grab sample detector actually can send a signal back to the analyzer as soon as an engineer or a process operator comes out and pulls a grab sample. So as soon as this opens and this grab sample detector starts sensing flow as the liquid starts moving out this way now, we can send a signal back to our analyzer that timestamps a collection at this sampling point right at this very second, so that the end user can look up the spectrum of the time-stamped sample from this sampling point and be able to correlate those grab sample testings in the lab to the online spectrum. So there's absolutely no confusion between, what sample belongs to what test result belongs to what sample, and what spectrum belongs to what sample. All of this is very nicely organized, time-stamped, and really helps this transferability of supporting a really nice hand-in-hand workflow between our labs and our process with our refinery customers. So just to wrap up and conclude here, thank you all very much for your attention thus far. The main point, of our HORIBA Process Raman is we can provide a direct Raman measurement of your process, which is super powerful with our 1 to 17 different sampling points with just one online analyzer. So instead of having several Raman analyzers for each sampling point, we can look at 17 different sampling points connecting back to just one of our online analyzers. Our detection ranges are best in the market for our process Raman right now. We can get down to single-digit ppm for very important components like sulfur. And then, of course, bringing that all the way up to whole volume percents, of course. We offer state-of-the-art chemometric modeling support. So we can really take that calibration and modeling labor off of your shoulders and off of your team. We understand that in 2026, more than ever, refineries are running on crews that are overworked, that are, don't have a lot of time. And, we want to be able to empower our customers and support them with these calibrations and chemometric models, and also train you on how to do this yourselves in an effective and productive way. Chemometric models are included for a year with the purchase of your online analyzer, so everyone can get trained up, can get the support that's needed. And we also offer support after that time period, of course, as well. Installation is rather straightforward. Just on average, about 2 days usually is how long we'll stay there, plus one more day of on-site training to make it about 3 days, half a week with our customers. But of course, we're not going to leave unless you want us to. And then typical maintenance, this is a real historical number, is about 2 hours per stream per year. And that typical maintenance comes from just cleaning the flow cell inside our flow cell enclosure. So thank you all again very much. We have a brand new HORIBA Process Raman website. We've written over 20,000 words of new content, not just on jet fuel, of course, but on all of the other solutions that we offer our customers with our HORIBA Process Raman. So please, I definitely want to encourage you to take a look at all of our new content and everything that we have going on. We're updating this daily. Just literally this morning, we updated one of our web pages on here. So please take a chance to look at this for more information. And then, of course, if you'd rather talk to someone, our team at HORIBA would be very happy for a phone call or for an email exchange. So please feel free to reach out to myself or Lance or our regional sales manager, Mike. Any of us would be very happy to get you, in the information that you may need or want for a solution. So thank you all very much. Everyone here at HORIBA really thanks you for your time. And please let us know if you have any questions that you would like to be answered in the immediate.
Thank you very much, Dakota. Stevie, are there any questions that we can't see, or are we good to go?
Hello, everyone. I haven't seen anybody submit any question through our chat box yet. Feel free to, if you have to ask any question.
Okay. All righty. Well, that sounds good. Again, as I mentioned previously, this webinar will be posted on our social media platforms here in the coming days. And if you do have any questions, or if you would like a quotation on one of the Raman products that Dakota mentioned, please feel free to reach out to us directly. Thanks everyone for your time this afternoon, and I hope you have a great remainder of your week.